Doing today's introduction is Dr. Patricia Pavier. Dr. Pavier is the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory. She's also the chair of the Gen 4 International Forum Education and Training Work Group. Patricia.
Good morning, good afternoon, good evening, everyone. It's a pleasure to be here with you. First of all, I wish you to stay well and safe. And as Berta told you, we're going to have 3 presenters today, so it's the first one. The first presenter will be Dr. Dasari V. Rao from Los Alamos National Laboratory. He's a nuclear and mechanical engineer with 25 years of experience in safety and safeguards of nuclear and high hazard facility. His technical areas of expertise include computational fluid dynamics, neutron and radiation transport, and risk assessment of nuclear energy systems. He has over 30 publications in this field. He is presently the director of the Office of Civilian Nuclear Programs at LANL. He is also the technical advisor to Dr. Jess Jehin, the National Technical Director for DOE Micro-reactor program, and he is the principal investigator for NASA's Fission Surface Power Project. Our second speaker today is Holly Trelu. She received her PhD in nuclear engineering from the University of New Mexico in 2003. She's a team leader at Los Alamos National Laboratory, the technical area lead for technology maturation for the DOE NE Micro-reactor program, and she has experience in reactor simulations and safeguards. Finally, our third speaker today is Yasir Arafat. He is currently serving as the technical advisor to the DOE Micro-reactor program from the Idaho National Laboratory. He has 10 years experience in leading and executing research development projects, primarily in advanced reactor development. He was the founder and technical lead of the Westinghouse E. Vinci Micro-reactor program, where he was responsible for leading the overall project design, technical and programmatic development of the micro-reactor designs. So without any further delay, first of all, I want to thank our 3 presenters with their enthusiasm to present to you this webinar. And I give you the floor, DV. Thank you again for volunteering.
Thank you, Patricia, for the opportunity. And I also would like to thank Patricia for taking on or organizing these fora. This is an exciting opportunity for us to present our vision and what we hope to achieve in microreactor R&D. And before I go too far, I also would like to thank Berta and, of course, others who has helped me put this presentation together, which is Holly and Yasser. So before we go too far, I kind of wanted to define what we mean by microreactors and the context. If you see at the bottom of my slide, that is the energy in terms of in keV or kV. So what you're talking about there is that that's the kilowatts. The nuclear comes in all sizes, all the way from sub-kilowatts, so hundreds of watts, tens of watts, to 1,000 megawatt electric reactors that are the standard. Most people are aware of the 1,000 megawatt electric plants. These are the big LWRs, such as the AP1000 units that are under construction in the US. Many of you are also aware of the next one, which is referred to as the small modular reactor, where each unit is small, but at the site, there are 12, 18, 24, whatever number of units, bringing it to about 1,000 megawatts. Other extreme is where Mars 2020 or various other NASA missions you keep hearing about. That's where you have jointly Los Alamos, INL, and Oak Ridge under DOE leadership have been producing the RTG sources. And those RTG sources are anywhere between 10 to hundreds of watts of electricity. So there is a big area between those small modular reactors and all the way MMRTG. The microreactors are, as a program and as a product, are designed to fill that gap between what's a SMR and what's a micro RTGs that are there. So the topic of discussion for us today is any reactors that are somewhere around, let's say, a kilowatt electricity to somewhere around 10 to 20 megawatts of electricity. There's a reason why we've done that, and one of them is that reactors in this particular energy range, they generally tend to have low volumetric heat generation and also have certain neutronic features so that you can actually control them much more effectively compared to reactors, especially the 1,000 megawatt reactors. And a vision here is that taking advantage of those controllability aspects of these small or micro reactors, we can achieve a lot in terms of remote operation at be it in space or at remote locations. So that's what drives the national interest right now. They can be, because they are so small, they can you can bring in innovative designs and make them through development cycle, make them affordable, and development cycles can be rapid. Both DoD and civilian industry is looking for reactors such as this to power the microgrids. Such microgrids may be to help provide resilience against storms or against cyber issues, all kinds of things. Or they could be simply renewable microgrids. And those are the national drivers that are really providing enthusiastic support to this effort. As we go through here, in addition to national drivers, the R&D that's being reviewed or being presented now has two other intersections. One is with the nuclear facilities. In particular, small startups do not have the nuclear facilities or access to the fuels or access to multi-year research programs that can give insights into new materials, be it nuclear materials or not. So one of the things that all labs are bringing to the microreactor program is so that private companies, small or big, can use the nuclear facilities that are at the labs. And finally, there is also the other intersection, which is that it really aligns with the science priorities of the labs and the nuclear industry, which is, can we accelerate the innovation? Innovation can be accelerated through additive manufacturing, can be accelerated through completely new way of thinking in how to enable heat transfer, or using new heat transfer methods or materials. These are all the priorities that have been there, and I think microreactors provide an opportunity to put them to test. So as a result, we view microreactor R&D right now as being the intersection of these three: national drivers, nuclear facilities, and the science priorities for the DOE and the industry writ large. Given that, what are the three things that we do regularly in that is we go out to industry and seek their input, and based on the input in a technology neutral way, we investigate information into investigation materials, fuels, or high temperature moderators, and we are also getting nuclear data on some of these materials. We are making prototypes, and the prototypes are to demonstrate, can we make advanced manufacturing? Can we embed sensors? And can we do demonstrate at different scales the ability to do simulation and experiment at the same time? In the end, we are hoping to come up with multi-scale nuclear validated codes and have test beds, and of course, also give access to National Reactor Innovation Center. All right, I'm trying to forward this. There. So let's go to a typical microreactor design. I'm sorry for that little interruption. It usually, the microreactors here could have high assay LEU. Some are using metallic fuel. Some are using ceramic, which is another way of saying uranium dioxide or uranium nitride or uranium carbide. And some are using trisofuels. So the research we are doing actually is to help all those designs. The second point of it is few companies are designing the reactors to operate in the fast spectrum, but many are operating in the thermal or intermediate neutron spectrum. And that is those choices are made in each case to suit their market niche that they would like to go into, as well as fuel availability. A fast spectrum reactor in general gives you much longer timeline, but you have to start with full reactor core loads of maybe a ton of HALEU, as an example. A thermal neutron spectrum may not give you such a long life, but it may give you, you can start off with, a few hundred kilograms of HALEU. Those are the type of marketing as well as product designs that the companies are making. A large reflector surrounds, that is the reflector in here. This is the core, and that's the whitish, at least lighter, that is the reflector. And usually the reflector is made out of either beryllium or magnesium oxide or a variety of different materials, depending on people's choice, again, the size, weight, etc. But it does two important things. One of them is that because these reactors are, in this particular case, criticality limited, the reactor only becomes critical when it is surrounded by the reflector. So you can put lots of controls, such as the control drums, control rods, etc., in the reflector, and you do not have to put or engineer the control drums, control rods, etc., inside the core. That makes core design and core fabrication and assembly much easier. And after, of course, it achieves criticality, heat generated in this core is extracted out either through channels that exist in here, so you can circulate air or molten salt or gas, or you can use heat pipes to transport heat from the core to a heat exchanger, and or in certain cases, whether there is a heat exchanger or it could be a direct Brayton as well. So structural material options for this type of designs or high temperature creep resistant steels. People are using molybdenum. People are using various other new and innovative steels that are being thought about too. And not only that the materials are new in some cases, but also the way it's made, such as using additive manufacturing and others, is being brought into this as well. So there are some companies that are looking at advanced ceramics or metallized ceramics, and some companies that are using graphite for the structural materials. Stuck again. Key technology enablers for microreactors, and this is in many ways make or break type of thing for these reactors. One of them is that those reactors and the internal components have to be factory built. What I mean by that is that building a reactor at a site, as we do today with the 1,000 megawatt reactors, that's very expensive. As it is, microreactor or economically, they become viable only if you could cut down the cost of fabrication. And factory building and assembly lines is the way to do that. Equally importantly, it also has to be easy to operate. What I'm showing here on the right is where, although I don't go into the details, a reactor that is operating at steady state, if for any reason the power draw needs to go down, which is what that yellowish line is, then the reactor power draw means how much heat are you drawing from the reactor so you can generate electricity. The reactor power should automatically follow. It's called load following. And how it follows the load and returns to stability real fast, that is the important aspect here. So the power draw going down, reactor needs to self-adjust power with very little need for controls. And in this case, 20% draw, and then another 40% increase. I'm just trying to show you that the reactor and the temperature of the fuels, everything else returns to safety with no need for any active controls. Now, these are kinds of things that we like to assure that the reactor can perform. That does not mean we are campaigning that there are no operators needed, but you want to figure out a way so that the reactors self-govern themselves and the operator and active controls become backup. And that is then they're easier to license, and that also means as part of the reactor development, we have to think about methods to demonstrate such self-governance. And a big part of test beds is to enable people to demonstrate that their reactors can do self-governance and that their reactors are safe, so that the regulators in return can have the confidence they need to license it. So what we do is we figure out various different ways the designs may be done, and we try to collate those challenges. But our R&D focus in the end tends to be concept and technology neutral, focusing on these type of things. Can you make this type of a core internal? How would it perform under intense temperature and cycling conditions? And is it controllable? Is it walk-away safe? These are the types of research that we are doing. Why is this research, and the importance of it is that in many cases, when original nuclear innovation was going on, I have this one slide where on the top left, you can see nation as a whole with three big companies, Combustion Engineering, Bettis, and CAPS. There were up to, if you actually pay attention, at any given year, they reached a maximum of about 18 criticality facilities in the country. They were of different complexity, all the way from zipper to places where they could actually demonstrate reactors, right? So we were at the time of innovation, we were driven very much by experiments, because behind that was the philosophy that unless you built one, you really didn't know how well it performs, because our computational ability to compute criticality and others was very limited then. And many people that are in the senior regulatory position right now have that background, that you should be able to demonstrate the technology. But over time, starting in 80s, the number of places where we can do experiments has gone down, but the ability to do computation has gone up. So now we really have very few nuclear experimental sites. And one of the things that we're trying to achieve through R&D in microreactors is what's the right mix for these two to merge, and where can we get away with just doing a limited amount of nuclear experimentation like the criticality benchmarks and others? Where can we get away with using non-nuclear test facilities, and where do you really need ultimately a nuclear demonstration? And what nuclear demonstrations can be done at the National Reactor Innovation Center. So that is what we are trying to put all those pieces together. And I believe we made a fairly good start, which Holly and Yasser will show you. But that is really the bigger challenge. How do we merge the theory with the experiments, try to bring along people that have always relied on purely experimental data to certify or to feel comfortable about their designs. Here is an experiment that we've done. It is the kilopower or Krusty experiment. And this one was done for NASA. It can be an example of types of things we could do in the microreactor. When I say we could, I mean the whole nation. I do not mean the 3 speakers that are here, or the 3 labs or the 2 labs that we're talking about. It is that we needed a solution for the reactor. We first figured out what are available resources and how do I buy down risk to first through how do I buy down risk by making smaller cores using existing facility. I can't wait to bring a new facility online. What can we do? The next is how do I bring in advanced fabrication and demonstrate that the advanced fabrication or the products that came from the advanced fabrication will actually take the stresses, thermal stresses, and all the rest of them so that you're buying down the risk. So the microreactors gives you an opportunity here to be able to do a engineering demonstration unit that is full scale. You do not have to compromise on that aspect because it is small enough. So you buy down the risk again until the last step then is a very limited amount of nuclear testing that you need to do that is actually demonstrates that it can load, follow, and perform. Lessons learned can be used to improve, but the idea is how do we make this innovation cycle, how do you shorten this cycle? And that's where we are, we hope through various design maturation efforts that are underway, we hope to demonstrate that. This is the crusty experiment, the so-called the Admiral test. Because we have gone through many of those steps I described to you, the crusty experiment we were able to do just for a few days and show in these cases, although I will not go into detail, the experiment is fully instrumented. And here when you start drawing down the power and are going up in the power, and you can see the fuel thermocouples, they self-govern, the reactor self-governs power. When you go down by whatever percentage I believe that's about 20%, in power draw, the reactor feels just a blimp and gets back to steady state, feels a little blimp, gets back to steady state. That's what we expect, the steady return to steady state. So you need very little amount of operator control. My colleagues Poston and Pat McClure, they are publishing much of these results in a journal article that is to come. But this is a demonstration of things that we can achieve as labs and as the community to shorten the innovation and to revitalize the nuclear. So with that, I've set the vision, and I'm actually turning to Dr. Holly Trellew. Though Dr. Trellew says she's just a team leader, I and the whole program counts on her to run this program, especially the tasks related to technology maturation. As Dr. Pavier introduced, when she introduced, she let you know that Dr. Trellew received her PhD in nuclear engineering from University of New Mexico. She's been at LANL, I don't know, forever. And it is my pleasure to introduce you my colleague and dear friend, Holly Trellew. Holly, please take over.
Thank you, Devi. Hello, everyone. I am Holly Trellew, the lead for technology maturation area of the DOE&E Micro-Reactor program, which involves working with a great number of people across the nation, including Devi and Yasser, but also others at many different laboratories to be able to work on these great challenges for microreactors. Today, I will be discussing some of the materials and technologies that we're researching. First, the fuel types being examined include uranium, molybdenum, and nitride, with enrichment up to about 19.75%, otherwise known as high-assay, low-enriched uranium fuel. Uranium oxide that is commercially fabricated with enrichment below 5% could also be of interest. Finally, metallic and TRISO fuels offer potential. As part of the DOE&E Micro-Reactor program, we are researching advanced moderator material to significantly reduce the fuel mass by slowing neutrons down and increasing the probability of fission, and thus optimizing energy production. Moderator materials that are being examined include zirconium hydride, which has a low neutron capture cross-section and optimal system performance, but suffers from hydrogen diffusion at temperatures above about 500 degrees Celsius. Yttrium hydride can retain hydrogen at higher temperatures and still offer good neutronic performance, and we will discuss that here in just a moment. Also, other alloys could be of interest. As in other reactor types, microreactors will have control, structural materials, and shielding. Because the system is so small, as Devi mentioned, we use a reflector to help contain neutrons within the core. Metal hydrides that are being considered in the microreactor program have been machined in the past, as shown in the pictures below, both for zirconium and yttrium hydride. Different techniques exist for the fabrication of yttrium hydride, including direct hydriding, which is well known and shown on one of the pictures to the left, and powder metallurgy, which is a promising new technique that produces stable material with fewer cracks, as shown by the sintered material to the right. Whereas these have been used some a little bit in reactors, such as zirconium hydride, and others have been used in the past, we need to develop these materials even further through some other programs, which we will discuss here shortly. The reason that we are researching yttrium dihydride is for its ability to retain hydrogen at higher temperatures than other moderator material. As shown in the figure to the right, where the hydrogen atom density is on the y-axis and the temperature on the x-axis, yttrium comprises larger hydrogen concentrations at higher temperatures than the other material. As you can see, water is listed on the chart. We also have other types of hydrides that really drop their hydrogen concentration, meaning that the hydrogen diffuses out or we lose it from the material as the temperature heats up in the system. To be able to produce power very efficiently in a microreactor, we would like to be able to operate as high of a temperature as possible. Thus, having yttrium hydride is a benefit for the system. Yttrium dihydride also has thermal stability compared to other metal hydrides, a relatively low thermal neutron absorption cross-section, and good elastic properties. There are some challenges associated with yttrium hydride fabrication in the fact that mere net-shaped parts are difficult to achieve for complex geometries, and large amounts of hydriding may result in structural degradation. In particular, we have some issues with cracking on occasion, but there are lots of different multiple fabrication techniques and advancements that have been made to reduce these concerns. The behavior of yttrium hydride under neutron irradiation environment is also something we are interested in. In particular, I apologize, the slides are lagging a little bit. We will be looking at tests of irradiation in research reactors, such as the Advanced Test Reactor at Idaho National Laboratory. Let me go back up to that slide. Past characterization on yttrium hydride has occurred for fresh material, but now properties such as heat capacity, thermal diffusivity, microstructure, elemental composition, and elastic properties will be examined through post-irradiation examination. For this particular test, we will be putting in various samples of yttrium hydride fabricated using both techniques, the powder metallurgy and direct hydriding, at several different temperatures and irradiating it for several cycles if possible. We will be looking at those results and characterizing the measurements at the end. Additionally, we will be testing the behavior of yttrium hydride through an integral critical experiment at Los Alamos' National Criticality Experiments Research Center. The goal of this experiment is to understand the transient reactivity feedback of yttrium dihydride, such as that the DB discussed earlier. High enriched uranium material will drive a criticality experiment, and a central region of yttrium hydride will be heated to various temperatures, and behavior of the system with and without the yttrium hydride at short timescales after startup will be analyzed. Beyond moderator material, we are exploring different techniques for heat removal from a microreactor system. Removal of fission heat from the reactor core will probably occur through either heat pipes or gas coolant, but possibly other options. Such heat transfer concepts include latent or a phase change of the working fluid, sensible or changes in temperature, and physical mechanisms such as thermoacoustics. In particular, we are initially designing non-nuclear test articles with heat pipes as the heat removal mechanism, but we will expand to other test articles in the near future. Yasser will be discussing some of our testing capability with which we will be placing these test articles to obtain data to help us with microreactor technological development. So the first test article that I will be discussing is a 7-hole stainless steel 316L monolith test article that will be used for single heat pipe experiments. These test articles of up to about ½ a meter in length comprise a central hole with a single heat pipe and 6 outer holes with cartridge heaters to simulate nuclear fuel. Both additive and traditional manufacturing techniques have been researched for fabrication purposes of these articles. 11-inch long additively manufactured parts are shown to the right, and they have been joined together using electron beam tear welding as shown in the picture at the bottom. These articles were fabricated with a laser additive manufacturing technique, a powder bed technique. And we did several different renditions of these to be able to understand the straightness of the holes, how it tapers a little bit from the plate up to the very top, and then technique methods that we can use to correct for that and come up with test articles that meet very low tolerances and will be used to produce data on a single heat pipe that we can use to help validate codes that we're developing through various programs. The next test article being fabricated is a 37 heat pipe, 54 heater design that will produce thermal output. As shown on the far right, a 1 meter long section of the core block would exist in the bottom half of the core with the heaters, and a heat exchanger exists in the top meter of the article. Heat paps span both regions of the core to provide heat removal capability to the heat exchanger. Fission occurs in the bottom half of the core, and in the top half of the core, the heat exchanger removes heat, which is sent to the power conversion unit. On the bottom left are machine parts with 91 holes for the core block regions and 37 holes for the heat exchanger regions. To the right are approximately 11-inch tall additively manufactured parts. Once these articles are completed, we will perform experiments with them in the non-nuclear test bed. In the meantime, we are performing analysis of these articles to understand their straightness and their ability to be joined. We are also analyzing various instrumentation and sensors for use in microreactors in conjunction with the Nuclear Energy Enabling Technology Advanced Sensors in Tile Instrumentation Program. Sensors initially being researched include thermocouples for temperature measurements, fiber optic and acoustic distributed temperature sensors, differential interface contrast for structural integrity, and other sensors for stress and strain measurement. I am now honored to present Yasser Arafat, who will be addressing the testing and demonstration areas of the program, plus other upcoming plans in the DOE Mini Microreactor program. Yasser, I will hand this off to you now.
Thank you, Holly, for the introduction here. Hello, everyone. This is Yasser from Idaho National Lab. Like DV, I'm currently serving as the other technical advisor to the DOE Any Microreactor program. Today, I'll be covering 3 short topics that you will find very complementary to what DV and Holly talked about, and it is the need for integrated testing and demonstration capabilities of microreactor technologies. And we need such capabilities because microreactors are essentially a new technology, and we don't really have any operational experience. And they're often phenomena that requires more than just modeling and simulation. And for such new technologies, one needs to perform what we call, 2 kinds of tests called separate effects test and integral effects test, both for standoff, from design manufacturing perspective, and also to answer regulatory queries. So today I'll talk about 2 of these test capabilities that we're currently working on that are designed to help industry developers conduct such tests. And finally, I'm going to wrap up on how everything we talked about ties into the overall DOE Microreactor program focus. Here we go. Okay, the first test stand that I'm going to talk about is called SPHERE. which stands for Single Primary Heat Extraction and Removal Emulator. So this test bed is designed to conduct separate effects tests, particularly on a particular heat removal technology. Although microreactors can be of many different types, nowadays we kind of see most of the microreactor designs are either heat pipe reactors or gas-cooled reactors. For either of these types of technologies, you can test what is happening at both the hot end and the cold end of a heat transfer technology, whether it be a heat pipe or a primary cooling channel. So it's a fairly simple setup. We have a quartz tube, which can maintain an inert environment using a combination of a vacuum pump and an inert gas supply, as you can see in the process flow diagram. We can simulate the reactor's hot end using cartridge heaters and heat removal through a heat exchanger that uses a cold water loop and has a turbine flow meter, a delta T meter, and about a 2.5 kilowatt chiller system. And with this setup, you can simulate almost any type of primary cooling technology. Now, when we started setting up this setup, the first test article that we are testing currently is actually a high temperature heat pipe. You can certainly simulate gas-cooled reactors as well using a primary coolant flow channel. Now, if we look into the next slide, besides sort of its fancy name, this rather simple setup has a lot of benefits and uses. First, we can conduct thermal performance evaluations of the primary coolant technology, like a heat pipe, for example, under a wide range of operating conditions. Second, which is, I think, in my mind is very important, is to characterize a particular coolant technology in various transient conditions, right? And take measurements like temperature, strain, during various operation modes of a reactor, like startup, shutdown, what happens during load fluctuations. Now, the nice thing about this setup is the chamber where the test article lies is transparent, and you can use different instrumentation and sensor technologies like thermal imaging and techniques like digital image correlation to look at what is happening to the test article. Things like displacement and thermal expansion. You can also simulate a heat removal with your particular primary heat exchanger type that's built into your test article. And then third of all, if there are any specific thermal coupling methods which are particularly related to heat pipe technologies, you can mitigate the gap conductance challenge. If you're developing technologies to mitigate that, you can basically try out different methods and test it here in this test platform. And finally, all the data that you can collect from here can be used to benchmark your modeling and simulation tools. So the next one that I want to talk about is basically a larger setup with yet another fancy name called MAGNET, which stands for Micro-reactor Agile Non-Nuclear Experimental Testbed. And using the magnet, we basically want to, quote unquote, attract industry developers and regulators to basically come to the test platform and perform what we discussed, integral effects test. This is basically a bigger and stronger version of the sphere. It's rated for a 250 kilowatt electrically heated micro-reactor test bed. And we're currently targeting to complete this setup by the end of the summer. It is currently located at the Energy Systems Lab here at Idaho National Laboratory. Now, this is a multi-lab effort where INL is basically taking the lead at developing the overall test platform. And as Holly mentioned earlier, LAML is working on a 75 kilowatt heat pipe reactor test article. This is basically a 37 high temperature sodium heat pipes with cartridge heaters to simulate fuel. And we have an integrated heat exchanger on the other end to remove heat from the condenser portion of the heat pipes. And we also have Oak Ridge, who's working on some embedded sensor technologies to diagnose what's happening basically to the test article and measure things like temperature, strain across the test article profile. Again, several benefits of this technology. Let me go back real quick here. This is obviously a first of its kind non-nuclear microreactor test platform that is capable of running integrated tests, so it's a pretty big deal. And we can look at an overall system performance, right? So on the right-hand side, there's a P&ID diagram of the system. I apologize, you cannot read much. It's very small writing there. I guess it was sort of intentional, so you can come and talk to us directly after this. I suppose I could explain this on a high level. So if you look at the P&ID diagram in the center, you basically have a vacuum chamber that houses the reactor test article. A pretty big chamber. If you think about it, it's a 5 feet by 5 feet by 10 feet. And this chamber can also get pretty hot. It's kind of built in a way so it has hydrocooling, which basically helps to maintain the outer cooling surface of the vessel. It has a very elaborate cooling loop that you can see in the system in the P&ID, with starting from a heat rejection, heat exchanger, which is basically in this location, a compressor to provide the motive force to drive the coolant around. That's at the bottom here. And by the way, the system can get pretty high pressure. We can achieve as high as 22 megapascals. So pretty much you can try out any different kind of coolant types and pressures. We also have a recuperator to preheat the inlet stream going into the test article. And one of the nice features in this system is that it's an optional connect for a power conversion. Now you can run the system without a power conversion, but if you have one, it's very easy to plug in to understand the overall system dynamics between your reactor side and your power conversion side. So what can we do with this? Let me go over some of the benefits here. First, it can simultaneously simulate the core and the heat removal sections. You can look at the temperature profiles and the displacements at various operational conditions. And obviously you can compare that with your modeling and simulation. If you have tried out any kind of a advanced manufacturing method to make a test article, this is a great setup to actually hook it up and test it. Same goes for a unique heat exchanger design. And you can drive almost any test article. If you want to drive it to failure, you can do that, provided you can clean up the mess afterwards. So if you're developing advanced sensors and instrumentation to achieve things like autonomous control, there are enough penetration ports in the vacuum chamber to allow for that, basically. The second item that I want to talk about is you can also look at and evaluate structural integrity of core sections like monoliths, for example, and other core materials to look at what's happening at the thermal side of things, like stress, deformation, to understand creep behaviors. Third, if you are trying to interface between heat pipes with both the core on one end and the heat exchanger, you can understand the dynamics between the two. And last but not the least, you can study cycling loading with a simulated reactivity feedback system, like we did in the past with space reactor prototypes, and DV has gone over some of that in the previous slides. So the most important part to me is this setup is basically technology agnostic. You can basically bring any test article and any power conversion system that represents your particular microreactor design, and we can learn this overall system behavior before we go ahead and build a nuclear demonstration. So now I want to just pull you back and shift your focus to like a 10,000 feet level and look at the bigger, broader picture. Let me go back to my slide here. I kind of jumped here. Okay, so I'm going to talk about now how this all kind of ties in together, right? So in this slide, I'm going to summarize what Holly and I and DV basically talked about and how they all kind of fit in to the three technical areas within the DOE any microreactor program. and that are shown on the left-hand side of the slide here. Now, even though we're currently working on all three areas in parallel, they do somehow align themselves in what I called a microreactor innovation pipeline, right? So if you look into the first area called system integration analyses, this is where when you have a concept, you look at the market research, you look at regulatory requirements, you do some integrated modeling simulation, and then identify the technologies that needs to be developed in the next stage. And that gets passed along in the technology maturation area. And this is what Holly primarily talked about. Currently, we're trying to mature technologies that may be useful for industry, like heat pipes, high temperature performance heat pipes, moderators that allows a reactor to run at high temperature but still allow moderation, advanced heat exchangers, instrumentation and sensors, things like that. Once you've matured those technologies, you can pass them along into the test beds that I talked about to see how they all together work synchronously in a single system. Now, that's the current focus of our program right now. Once we have achieved that, eventually what we want to get to is shift our R&D focus to the R&D needs for microreactor application demonstrations. Things like hydrogen cogeneration, how do we do district heating, what are the R&D challenges required for autonomous operation, remote monitoring, etc. And as my last slide here, as a conclusion slide, I want to take you back to what Devi was talking about in the first slide of how all this effort and work that we're doing help us achieve, right? What does it basically help us achieve? All the R&D that we're currently undertaking is geared towards fulfilling these three basic notions of what defines microreactors. First, they're factory fabricated. I mean, they're entirely fabricated and assembled in a factory. So the question is, how can we design microreactors to enable ease of factory fabrication? Can we use things like advanced manufacturing for that mission? The second distinguishing factor is basically that microreactors are transportable, and they are transportable typically as a single, fully assembled unit. Some of them are actually considered mobile, where they can move from location to location. The question is, how can we achieve all these challenges associated with the transportation of a fully assembled and fueled reactor? And lastly, microreactors are supposed to be self-regulating, so we don't need to worry about controlling it for safety or for operability, so we can make them somewhat walk away safe to the point where we don't need any more operators, right? If we can achieve all of that, we believe that microreactors can truly redefine how we generate energy using nuclear. And in the current DOE Microreactor program, it's a very focused program. We're not trying to tackle everything, but we're trying to undertake the most challenging and impactful R&D needs that national labs can work on that can accelerate the deployment of microreactors as quickly as the mid-2020s. And that marks the end of our talk. Thank you all very much for listening in today.
Thank you, Devi and Holly and Yasser. If you have questions, please go ahead and type those into the Q&A pod. I see that there are some questions already in there. While people are still typing in those questions, we'll just take a quick look at the upcoming webinar presentations. In April, a presentation on the GIF VHTR Hydrogen Production Project Management Board. In May, performance assessments for fuels and materials for advanced nuclear reactors. And in June, a presentation on the comparison of 16 reactors, neutronic performance, and closed thorium, uranium, and uranium plutonium cycles. So the first question, Devi, let's take the first question directed to you. Dr. Rao, what is the thermal and electric power output of a microreactor? The IAEA has defined small modular reactor, but not microreactor.
We have at the start of the effort, spent quite a bit of time looking over what could be the range over which one would call it to be a microreactor. I think we generally settled that first, let me talk you through how we came up with the limit and why the limit by itself may not be the biggest discriminator. It's what makes a microreactor that's the discriminator. We envision a microreactor where reactor system should be self-governing and walk-away safe. In other words, what are the features of the reactor that provide ability to control the reactor with controls located outside the reactor, the control drum, etc. And what are the features that are required so that the reactor can self-govern and is walk-away safe. In other words, there is, even if the control is lost, it reaches a steady state where it's just generating enough heat that can be compensated by the losses through radiation and others. Approximately, these features can be met when the reactor power is limited to somewhere around 20 megawatt electric or less. Higher than 20 megawatt electric, you could get a reactor, microreactor with these features, but they're extremely difficult to perhaps design and operate. So for the microreactors, we typically refer to them as anywhere from, few kilowatts or hundreds of kilowatts to a maximum of 20 megawatt electric. And that is our definition, if I could use the phrase very loosely, of the microreactor.
Thank you. There's a question. There are a lot of companies that claim to be working on the development of a microreactor. Which companies are actually close to bringing one to market?
This is, let me take that, and then maybe I'll also defer that to Yasser and others. There is one company that has very recently, as in last week or last 2 weeks, filed a licensing application. It's called COLA to NRC, and that company is Oklo, and the product name is Aurora. And there are few other companies that are actively pursuing, as you can probably saw in a recent announcement that 3 companies were listed there, one of them being Westinghouse, the other BWXT, and a third yet was X-Energy. These were listed in an announcement by Department of Defense. Other than those, there are various other companies. However, NEI, that is the Nuclear Energy Institute, perhaps is the better source for who is closer to releasing a product. I personally do not have that knowledge, and either Yasser or Holly, if you want to take that, I welcome your contribution as well.
So Divya, I don't think I have any more to add besides what you've answered. I've seen as high as 15 microreactor developers just in the U.S. And Canada, between those 2 countries. You've mentioned the ones that are more on the mature side of scale, but there are different other microreactor vendors. Some of them are early developers, some of them are also pretty matured. NEI report is a pretty good source to look into. There's other references where you can look as well to understand who all are playing this. So yeah, there's actually it's actually a very good thing. There's a ton of developers out there that are working on microreactors.
Holly, do you have anything to add?
I do not have anything. You covered it well.
The next question. In the case of uranium nitride, is the nitrogen natural N14 or highly enriched N15?
Great question. I think people prefer to have enriched because of the lower neutron cross-section, absorption cross-section, that is. However, until that resource is available, perhaps the first set of reactors that use uranium nitride will probably have regular old atmospheric nitrogen. So natural.
Great.
I just want to add a little bit to that question. The supply of enriched nitrogen is somewhat of a demand supply issue. Right now, I think the nuclear industry pretty much is one of the only industry that is wanting providing a demand signal for that. There are technologies or companies out there, particularly the ones that supplies compressed liquefied gases. They have the technology to enrich nitrogen, but it's all a matter of demand and supply. If there's enough demand signals created from our side, there could be suppliers that are available to provide that in the future.
We're going to do reactivity criticality tests at 1,000+ degrees Celsius where they operate and hydrogen is more likely to migrate.
So I can try to answer that. I'm not sure that we're planning on any tests above 1,000 for the most part. So the
yeah, I was going to say that.
Experiment, that I presented will be at 335 Celsius and below. There are other tests we can perform on materials at higher temperatures, but yes, at some point when the high-grade hydrogen migrates, we have to make sure that's done safely and in a different environment to see. We've done some tests where we look at the yttrium hydride and we try to look at the vacancies that is in the material at just a small amount of time at a higher temperature so that we can start understanding where those problems might occur before we design bigger tests.
I was going to add to that is there have been experiments done way back in the nuclear aircraft days. Whether hydrogen leaks out of yttrium hydride at 1,000 degrees or more depends on the stoichiometry of hydrogen versus yttrium. For example, if you have to have a yttrium to hydrogen stoichiometry of 1.2, I don't believe too much hydrogen comes out at 1,000 degrees Celsius. But that is a design knob that the designers have in their arsenal to design based on what's the temperature that they expect to go to, both regular as well as off normal, and what do you give up by going lower stoichiometry. Next question.
Additive manufacturing should be assumed for future core design, but comment on the issues. For example, is laser powder bed fusion safe, or will the laser negatively affect the fuel? Can in situ monitoring be depended on to ensure acceptable fuel characteristics? Are mixed materials suitable? How about ceramics and a metal matrix? How about built-in instrumentation?
I will take the last one because the first few of those, I simply answer that that's what the research program hopes to find out. The last one, that is the metal ceramic, is of interest to many for the structural materials because you could embed sensors in the metal ceramic matrix. And realistically, when you want to go up to temperatures of interest here to, as previous question was 1,000 degrees Celsius, etc., there are very few metals that you can rely on. So sorry. So I think that is something we are going to study, and we are studying, and that's of interest. Maybe others can take the questions on the post set of things, but those are topics of interest to us. I don't think I have any insights into the actual, any research insights.
So the question on the powder bed and additive manufacturing, right now additive is just being used, this is part of the research is to understand what type of material it produces, how structurally stable that is, and that is just through non-nuclear testing and not involving the fuel at the moment. So we would have to research how it performs in the fuel environment later. The other part about instrumentation, yes, we are looking at in situ monitoring other types of sensors to help ensure those characteristics. One of the challenges we have with especially an integral micro-reactor system is if it's built initially and we can't get in very well to put sensors in later, we need to think about that during the design process, is understanding what we can put in there to see neutron counts and or other parts that are going on in the system, the integrity, stress and strain. All those portions are things that we're researching.
Thank you. Anything to add, Yasser?
Nothing to add there.
Okay, great. We have quite a few questions now. The list is getting longer. What about the needs and time for R&D testing and for fuel side of microreactivity?
So can you repeat that?
Can you repeat? Yeah.
What about needs and time for the R&D and testing for the fuel side of microreactors?
So I'd like to take that question first and then turn over to others. One of the advantages, if I could call it, of many of the microreactor designs we are looking at, they typically have very low burn-up, and as a result, the fuel data that we need for many microreactor designs, the fuel itself, that is well characterized from other programs, unless, of course, the fuels to be talked about are some things like molten salts and others. There is some data that's needed. So as of right now, our emphasis has been on, can you make the fuels and provide infrastructure so you can scale up fuel production? That's more of an emphasis than what data do I need to qualify fuels. But I could be corrected, and I'm going to turn to other two, Yasser and Holly, if they want to add something.
Yeah, maybe I want to add to, so as far as fuels are concerned, the majority of the microreactor developers that we're seeing right now, they're trying to leverage all the work that has been done in the nuclear industry for the last couple of decades in fuel development. So they're trying to maximize that effort. And so we've seen folks using metallic fuel. Most of the reactors that are being looked at by Strategic Capabilities Office that DV mentioned in an announcement last week for the mobile reactors, those are trying to leverage all the work that has been done in the AGR program on TRISO fuel, which there's been a lot of work done in the past to qualify that fuel. So all in all, they're trying to leverage what has already been done overall. And as DV mentioned, I think the focus is primarily on the deployment side of things rather than on the development and the R&D side as far as fuels are concerned. So people are trying to focus on the production levels more than how to develop a new fuel from microreactors.
Holly, any last thoughts?
I do not have any more comments beyond what they said, besides that is something that needs to be focused in the long run as we start trying to, I mean, vendors are going to have to take that into account, in particular in designing their plans to be able to get a system operational. We will support them as we can.
Economics. How affordable are MMRs compared to conventional reactors?
DV, do you want me to take that?
Yes.
Okay.
Please.
So microreactor economics is a very complicated topic, but in a nutshell, the way most of the vendors are trying to look at microreactors, obviously there's a lot of pros and a lot of cons when it comes to economics of microreactors. But in summary, in general, microreactors are being sought to initially be deployed in non-grid-tied applications where AP1000 type or large-scale nuclear power plants are currently providing electricity. Rather, microreactors are being looked at for niche applications like decentralized generation. Now, why are they doing that? Because it is essentially a new technology, and like most new technologies that are deployed, they are going to be expensive. So they're trying to tackle markets that pay higher amounts of dollars per kilowatt hour for energy. So things like remote communities, islanded communities, some commercial remote, industries like mines, for example, some defense applications that requires high resiliency. They actually pay a higher premium for power. That's the initial market entry. The thought and the idea is once they are feasible and they are able to reduce the cost, and they can tackle other more mainstream energy markets once they're able to bring the cost down. But initially, most of these applications, and they are going to be, based on preliminary numbers, they look very competitive for some of the unique applications like remote communities and others. Maybe DV and Holly can add anything to that.
I have nothing to add.
Yeah, I do not. I think we usually rely on those. You are the expert in those things.
I would encourage you.
How would the waste management methods differ from conventional large-scale reactors?
This is Holly. I will start with that.
Go ahead.
If you want.
No, I was going to refer it to you.
Okay. One of the things that certain designs have included is once you put the fuel in there and you do irradiation, it is again all contained within one vessel or containment area, is that we may not get to the fuel at the end and it would all be disposed as one big unit. So that would have a little bit, extra volume, but because of all the extra shielding and things that are involved, that may make it safer to do something such as bury it underground. Now, that being said, only certain designs may look at that. Others may have ways that we need to pull the fuel out in the long run, and it would have to be treated as any nuclear fuel. The burnup may not be as large as in conventional large-scale reactors, and thus we would just have to treat it a little bit differently. That's all I have on that.
I have nothing to add.
One thing I would add is I think the, let's call it refueling strategy, is a matter of what the customer is willing to take on their sites, and also economics. right? So if the economic allows, the easiest thing to do, as Holly mentioned, is to replace the entire reactor section, which is, the reactor, the reflectors around it, the control systems, all of that. And it is somewhat in a similar package as to how we store currently, LWR fuels in dry casks, right? They're similar configuration, similar geometry, similar heat load. If the economics does not allow, and there are benefits to recycling most of the other parts of the reactor besides the fuel, that is something that often, some of the vendors are looking at to perform refueling, not at the site, but at a central location like a factory, where they would transport the entire reactor, pull out the fuel, put new fuel in, and send it back to the site or a different site. So there are different strategies, and again, the drivers are not technical, but rather, on the marketing and the economic side of things.
If I were looking to test a reactor design in sphere or magnet, what information would you need, Yasser?
So we would like to know what the dimensions obviously are, what kind of a thermal power we're going to mimic as power inputs. We would also like to know what types of instrumentation and sensors that you would like to use, so we can understand if we have enough instrumentation and sensor portals in the chamber. So basically rough parameters like, what are your cooling conditions, for example. That will help us understand what type of a gas we would want to use to extract heat out of the test article. So just those high-level parameters. If you have any additional specifics, feel free to reach out to me directly, and I can certainly, provide context to the subject matter experts of the magnet and the sphere, and they can certainly give you a list of parameters that they would like to know before you go ahead and test it. And the other thing is, obviously, there has to be a development of a test procedure, which will have to happen between you, who's bringing the technology, and us, who has the platform, sit together and then figure out what are the test procedure look like overall. So feel free to get in touch with me directly.
Right. This is Devi. I just want to add one thing. Before, there are two other people that I'd like to acknowledge, especially any of these decisions related to how we would do the testing. One of them, and I bet, I don't know if they even joined in because it's such an early call, but Jess Zine, he is the National Technical Director, and also, of course, the DOE, the sponsor for this, is Tom Sawinski. The reason I'm giving you those names is so these decisions on how to engage with the industry and what's the best way for us to engage with the industry, etc. I think we will provide you all the technical data you need, but they both will have a final say on those things. And I also want to thank them for all their hard work.
Absolutely. I'm not exactly sure why I've lost the video, but I do believe the audio is still functioning. So bear with me, please. If I can, here we go. That was very bizarre. That's a new experience for me. So hopefully we are still online and moving forward. So Dr. Trulou, how long do you plan to run the ATR test for the YH, the yttrium hydride, to check the hydrogen diffusion from the material?
So the initial test in ATR will probably be just one cycle for the first one, And then we would like to plan 2 or 3 cycles beyond that, which is 132 days would be 2 cycles. But initially, I think we'll pull them out after probably about 60 days and just look at the initial performance of the material. Then if we need to design things further on, we will do that.
Will new reactors require a special training for operators? Is it a part of the microreactor development program?
You know, that is a question that we haven't come to cross yet. The reality of it is that, well, there are certain times the questions come for which I don't have an answer, and this is one of them.
Maybe I can add a little bit to that. So currently, our focus it has primarily on the 3 areas that I talked about. We currently do not have any work packages related to operator training. Now, having said that, there are other DOE programs that are, very recently put in place, like NRIC, for example, that stands for National Reactor Innovation Center. They are primarily in place to help with things like this, like not only just demonstrations, initial demonstrations on DOE sites, but also, how does some of these initial demonstrations facilitate things like, operator training, etc. So between, and again, the NRIC and DOE Micro-reactor program are very tightly integrated. So going forward, I think both these programs will be working together to, as we go closer to demonstration, we will be working towards getting some operator training exercises done.
How do you simulate reactivity feedback in electrically heated test core?
So actually, there are a couple of papers from the past. An example of a paper was by Shannon Bragg-Sitton and others when she was doing her PhD. But a quick review of it would say that you first want to have a quick running kinetics model. It could be multi-point kinetics or point kinetics or others. And you figure out a priori what the power distribution in each pin or in each area, spatial area of the reactor. And you provide thermal heating in terms of electrical heating or induction heaters, etc., at that location, and they are precisely controlled, and they can then be turned on and off and ramped up and down the power using the point kinetics or the kinetics model. It was very effective in tests, and that is actually one of the biggest advantages of the microreactor is the reactor core is small enough that you could do those experiments very precisely even. Yeah, like I said, if you look under Shannon Bragg-Sitton, she was the primary author on that. Articles from 1990, early 1990 or mid 1990s, or maybe 2000 actually. You'll see those articles. And we also have additional articles that are LANL reports on that. I'm sorry, Los Alamos National Lab reports on that, on uncertainty assessment and the difference between EDU, that is the engineering demonstration unit, and the nuclear demonstration unit, and how do you scale up and down. So there's a lot that was done on that. And the key principle still is you use models to figure out where you want the energy, how much, and what its transient should be a priori, and you simulate that, and then you qualify the component that it performs well. Anybody wants to add?
No, I think I couldn't have said it better.
How to perform how to perform core self-governance, use of artificial controlling units?
No. It's one of the things that, well, first of all, yes, you could do that. That makes your certification and others then will be driven by the software certification. But the most important aspect of microreactors, if they are designed right, is that, as many nuclear engineers know, reactors themselves are inherently self-governing. That is, when you design it right, as the temperature goes up, the reactor criticality goes down, and vice versa. As the temperature goes down, criticality goes up. So as the power is drawn more and less, the reactor, the materials, their expansion, their cross sections, you design, amplify those features and time them so that self-governance is done naturally by the mechanisms that are inherent to the reactor. For example, in a fast spectrum reactor, as you start operating at a steady state, let's say your turbine trips, that is, you're not drawing any power from the core. What happens immediately is that the reactor heats up. And during that heat up, the reactor core expands ever so slightly. And that expansion is enough for the neutron leakage so that the reactor becomes subcritical. So reactor is no longer generating fission power, you're just removing the decay power. And that situation reverses when the temperature matches back to, and the turbine comes back up, and the reactor starts cooling down. Once again, the reactor contracts, and you reach steady state. So this type of a mechanism is what we refer to as self-governance or inherent load following. Sometimes you may use an artificial control to actually enhance or amplify that, but a lot of times these reactors are designed with that behavior in mind, and they do it with advanced modeling and simulation tools. They figure out a way to time these feedback mechanisms and amplify them. That's what self-governance is. Anybody wants to add?
No, not particularly.
Is heat pipe failure an expectable event during the operation life of a microreactor? What would the consequences could it bring? For example, sodium leakage, thermal gradients on the monolith, etc. There's actually a few questions on the safety, such as that one.
Okay, so let me take that particular question. In the life of a reactor, a reasonably well-designed heat pipe, sodium or sodium potassium or potassium, we don't expect to fail. However, that does not mean we don't design for its failure. In case of a failure, most failures that are known for heat pipe, so for those of you that are listening in, a heat pipe has a 3-meter long heat pipe, for example, about 1.5, let's say 2 centimeter diameter. That heat pipe can extract about 7 kilowatts of thermal energy, and it has less than a tablespoon of sodium. So sodium release, first of all, is not the mechanism for the heat pipe failures. Heat pipe failures happen mainly because the wicking gets lost. It gets cradded or corroded by sodium if you didn't clean the sodium right. So sodium release is not an issue. Even if sodium is released, a heat pipe contains very small amount of sodium. So let's put that aside. The way any reactor is designed, or should be designed for the heat pipe reactors, is that we call it delta failure. That is, the heat pipes in the closest 3 heat pipes forming, let's say, a delta shape or the triangular shape, they fail. You still should not have any failure of the fuel. You may have to lower your power level so that the thermal stresses and others are not a major issue, but it should not lead to any exceedance of either the fuel temperatures or the monolith performance temperatures. That is a basic fundamental aspect of heat pipe design that at least we follow at Llano, and I'm pretty sure good engineers all across, that's the kind of safety they would use. I turn this over to, and by the way, one of the experiments that Yasser and others will be doing in the near future is actually creating these failures. As Holly described, in the test bed that we are standing up, we intend to fail the heat pipes and see what happens to the stress and strains of the monolith. Anybody want to add?
Yeah, this is Sally. The only addition is that, yes, we've looked at modeling what the failure of a particular heat pipe will do to the temperature in surrounding heat pipes and looking at some of the thermal stresses. So the main thing is if one is not removing heat, the power that's going to be going to the others around it will increase, and we have to make sure that it's in the design margins to be able to handle even a 30% increase or something. And that's part of the safety analysis that will be done in the design process.
One thing I want to add about heat pipe failures in general, and I want to acknowledge Dr. Bob Reed, who's like, in my mind, the world expert in heat pipes at Llano. We've had a very short course recently, and he talked about some of the failure mechanisms on heat pipes. One is you can break the heat pipe cladding or the pipe itself, either through different stresses or other mechanisms, or if you have impurities within the heat pipe itself in the form of oxides. Now, the term failure, it's a little bit black and white when this question arises. I think if you look at some of the data, there's been a lot of testing done with heat pipes in the last couple of decades. And if you look at some of those experimental work, there have been very few failures, and a lot of them were associated. And I want to point to a very quick example. There was an instance where one of the pipe had a puncture on the heat pipe, and that was due to some external particles or oxygen moving in from a quartz tube into the tube. But even though there was a puncture, the heat pipe continued to function as normal due to the liquid surface tension, right? So there's a lot of work that needs to be done to understand what heat pipe failures, what the real mechanisms are, and what the consequences look like. Do they fail in their function, or do they, what are the failure modes in general? So that's an area that we're trying to actively look into through the program in the near future to understand what the failure modes and effects analysis look like for heat pipes.
And also to add, yes, thank you, Yasser. The other part to add on safety in general for one of these systems, these are designed with very low amounts of fuel relative to commercial reactors, and types of thermal power that are designed for these small systems have been tested in instant space reactors or other technology in the past. We will, of course, be making sure that those rates and things to the public will be as low as possible, with shielding, with other types of containment. And the goal in some of these cases is to put them in applications that are remote for the most part. So we would have even design it such that if people are walking around outside, the risk to them is very small. And of course, looking at all sorts of different failure modes within the system, such that if something does go wrong in the core, we're going to have shutdown rods that will be inserted that will shut down the reactor and keep more fissioning from happening, and then other types of systems designed within the thermal loops that will be developed. So yes, convincing the public is important, and that will be part of what we will be, we meaning the whole nation, vendors and or any other programmatic support that we have will have to address.
Thank you. There's two that are on a similar discussion. What is the length of the longest heat pipe manufactured in industrial maturity? And the what is your best coupling method of heat pipe to source or sink?
Maybe I can take the second one. Maybe Holly can take the first. I don't know. I'm not trying to
let me do the first. Let me do the first one, and then perhaps we can hand off. The longest heat pipe is a difficult thing to answer because Alaska, I think, has been operating a heat pipe that is several hundred feet long, and the longest that's operating at Lanel, that's an alkali metal heat pipe, is about 30 or 40 feet in that range for a solar farm, solar thermal. In reactors itself, we are kind of looking about somewhere between 2 to 3 meters long in the length of the heat pipe. The dimensions of the diameter is about 1.5 to 2 centimeters, or maybe sometimes even lower in diameter. And the throughput tends to be, if it is a single-ended heat pipe, about 5 to 10 kilowatts in that range. I'll turn this over to Yasser regarding the the bonding, thermal bonding, etc. Yasser, it's yours.
Yeah. So I do want to. Let me focus first on the problem or the challenge first. I think the heat pipe is a solid heat transfer component. Typically, it is connected both on one end to the core, the other end to a heat exchanger, which are typically solid components as well. Now, turns out, if you make everything using the same material, for example, then the challenges are smaller because they expand. Their coefficient of thermal expansions are very similar, but a lot of the times you don't have the same materials. So either you're bonding with a ceramic or a graphite or some other steel material or metallic parts on the core side and the heat exchanger side, which have different CTEs. So as you're heating up from room temperature to operating conditions and also in some transients, you are going to have that gap, conductance change over time with the gap in between the heat pipe and the source and the sink. There are multiple solutions that industry and the lab, complexes are looking into. Obviously, if you look into the solutions, there's a solid bonding materials that people are looking into that can bridge that gap. There's people just, folks just leave a gas gap in between, which has a, somewhat of a high thermal conductivity like helium. It's not as great as a solid gap, but it does some of the job. And then the last thing is a liquid gap. The liquids gap one, it all depends on what orientation the heat pipes are. vertical or horizontal. It's a bit more challenging on the horizontal side, but there are other ways folks are looking into to keep the liquid in there that allows this gap to change, and the liquid will adjust to that, but it will prevent the liquid from flowing away from it. So there are different solutions being investigated. There isn't a one single answer for that. There are multiple, and folks are looking at that right now.
Thank you. Holly, do you have any thoughts on that?
I do not have any further insight.
Okay. Which type of power conversion system is more suitable to microreactor? Brayton cycle, stirring engine, or Rankine cycle?
Maybe I can start with that.
There are three of us online. I think there will be 4 opinions on it. So, yeah, why don't you take that, Yasser? I think.
Okay.
Yeah.
So maybe Divya and Holly can supplement this. But on a high level, I think there's not a correct answer on which one is the best one. It all depends on what your reactor technology is, what is your operating temperature, and how you want to integrate with the power conversion system. So if you look at Stirling engines, for example, I'll just talk about the power conversion technology itself and some of the challenges associated with the integration. Stirling engines typically are somewhat mature technologies, but they're small power level and their power densities are small. So if you're looking at a very, very tiny microreactor, that could be the way to go because they're self-contained. They are frictionless parts, most of the engines that are commercially available. So that's a suitable technology for very, very small microreactors in the kilowatt maybe range. If you go to larger systems, both Rankine and Brayton systems are feasible. It all depends, again, on the temperature range. If you're working at medium temperatures like around 300 degrees Celsius, Rankine works. But most of the microreactor initial applications you're looking into are trying to come up with solutions for Alaska and the Arctic and some of the extreme environment conditions. Their Rankine systems don't really work very well because they freeze up. For those applications, gas-based Brayton systems work. And again, even in the gas Brayton systems, there are 2 types. One is a closed system. People have looked at helium Brayton systems or SCO2 systems. And there's open Brayton systems, which basically use air, ambient air, to be pulled into the power conversion, get the heat from the reactor, and then basically drive a turbine to generate power. They all have their pros and cons based on efficiency, size, complexity. So I would say in general, for larger microreactors, gas is probably the way to go. For very, very small microreactors, Stirling is probably the way to go. But again, it all depends on what people trade off with their design parameters.
So I'll add to that is that Lee Mason, he's an investigator at Glenn Research Center in NASA, has looked at this much systematically, and the answer really doesn't change much from what Yasser said, but it provides you a structural way of looking at what power range and what system is best. If your issue is with the weight, you have some options. If your optimization is energy efficiency, you may yet have a combination too. Don't forget that some of the gas cooled system could be, cogeneration along with coupling to water. So I think there is a lot of innovation on power conversion that needs to happen. And believe it or not, I strongly believe that microreactors is one way for us to open up that area for power conversion vendors to get their innovation going in this power range. I'm done.
Thank you. We still have probably 15 questions in the queue, so we may not get to them all, but perhaps we could follow up by email, split them up or share them, and you could respond by email. We could post them on the GIF webpage. There are several questions related to security and malevolent, malevolent acts. Do you want to just take a high perspective discussion of that?
I can discuss that briefly. Yes.
Please do. Yes.
So one of the topics we're looking at for security on these systems is, again, it's harder to get into the actual core to do traditional materials accountancy measurements, neutron and gamma. So a lot more will be based on physical security, designing tampers or other indicators that the system has been breached by any point. Also making sure there's enough physical security. If this is a mobile type of power source, we need to have enough people around protecting it at all times and treating it just as you would any type of material during transportation. Those are some of the things we're looking at. And again, if you're going to be putting this, instead of having a big commercial power plant with fences, you may have to design something that would be, you could construct at whatever point you are out into the field, that you could actually put up whatever physical security measures are needed at that given time. So it's just a different type, it's the same general concerns as any reactor, but how we implement it still needs to be researched.
One, I think, clarification that's worth mentioning on that front is that concerns qualitatively are same, but quantitatively in some reactor designs that I've seen, that I've done, net amount of fissile or plutonium produced and at the end of cycle is less than the SQ quantity. So that's a bigger difference too, is that you're not expecting to have in each of these microreactors very large amount of plutonium to start with. So additional features are all important as well. Now that is not to say there will be no microreactors that would have that, but in general, because they're lower power levels, etc., they do not have as much plutonium at the end of cycle as you would expect in other reactor on a quantity-wise power reactor. But otherwise, I completely agree with what Holly has said. Any other questions?
Bear with me here, sorry. Dr. Alwyn, you were talking about transportable. Does it mean transportable only before installation? If it is so, the benefit should be very limited, save several months of time. If not, how do you concern about the shielding after operation, which would be very heavy to be transported?
Very heavy, yes, but I believe in almost every design they will make those decisions. But I have looked at and I can think of reactors in the, let's say, in the 5 megawatt electric range. They operate, and after you shut down and you wait for a week or two, maybe about a month, your direct radiation from the reactor can be easily handled through shielding and they're transportable. A lot depends on the logistics of how one chooses to transport and what type of shielding they like to attach. But considering that there are trucks that can these days are multimodal that can move around, 50, 100 tons. I don't expect the shielding after to be the biggest issue. I'm not minimizing the technical challenge. I'm just saying I don't believe it's a problem that's not solvable, if I could use the phrase.
Yeah. Just want to add to that maybe. Typically, for microreactors, shielding is broken down, or I would say the physical shielding is broken down into two functions necessarily. The first one is for normal operations, which typically does not involve integrated shielding. The integrated shielding is typically used for when as DV mentioned, when you shut down, you wait for a few days, whatever gamma level that you have left, you can have integrated shielding to mitigate that to stay under the 10 CFR. I forgot what the 10 CFR 20, I believe, is or 71 limits. The majority of the challenges regarding shielding is during normal operation, and folks have used different methods for that due to the high neutron levels. You can have concrete barrier around the reactor, or some have had designs to stick it into the ground to have inherent shielding. So essentially, for normal operation and after operation, you break those shieldings to integrated and in situ shielding.
Is there any customer other than DoD or NASA involved? NASA, I guess you should say.
I will leave that to Asser. He looked at that much more than I have. I have been following those two, DoD and NASA, and we do get some requests for information from many university campuses and others. But Asser, why don't you take this on, please?
Yeah. So as far as the customer base, besides DoD and the defense side of things, on the commercial side, the majority of the customers seeking microreactors are the ones that are using diesel generators. Like if you look at some of the remote communities in Alaska and northern Canada, there's a lot of communities out there that currently use diesel generators, and it's not a trivial amount of market compared to the size of each microreactor. That's relatively a very big market. For example, in Alaska, there's 200 plus remote communities that use diesels. Same in Canada, there's about roughly 200 plus megawatt power needs. There are also islands and like Puerto Rico and other areas that also rely on diesels that are trying to look for alternate technologies because importing liquid fuel is very expensive. So to summarize, there are a lot of customers, and we have had conversations with some of them, both on the government side of things and also from the utility side of things as well. So the answer is yes, there's a huge market base, even for the initial deployment, I would say.
Well, I'm being signaled that we're about out of time. There are a handful of questions that we didn't get to, but if we didn't answer your question, please be patient. We will follow up by email, and I will share those written questions with each of our presenters, and we'll respond by email and post at the web page. Again, thank you very much, DV, Holly, Yasser, for your time and expertise in sharing everything that you know and putting together such a marvelous webinar presentation. At the end of 2 hours, we still have over 115 people in attendance, and that's remarkable.
I will just add to that 3 thanks to, of course, you, Berta, and Patricia. And if Jess got himself out of bed, and if he's there, just Jean, And I don't know if Tom Sabinsky is dialed in. I do not know that, but if he is, Tom, thanks for giving us the opportunity. And it's a very exciting area, and thanks for all this opportunity.
Patricia, any last thoughts? I know your phone is dying.
Yes. Do you hear me?
Yep.
Okay. Yes, I wanted to thank you, Divi, Holly, and Yassir, and it has been really a great turnaround. And thank you for your expertise. Again, these webinars are archived. I really encourage you to go back to www.gen-4.org. All our webinars are archived, so you can watch them and you have access to the PDF file. Also, we have a survey. Let us know if you have other ideas for webinar topics. Thank you again, the three of you, for a great presentation. Stay safe.
Yes, and thank you, and thank you for everyone in the audience and everyone else who supported the program.
Okay, bye-bye.